Test, test. So have you tried assignment one? Started, okay. So do you have any questions or doubts? So far, no? Oh, a bit? Yeah, you can ask me during the break, and you can also come to the help session. I just sent a notification today. Yeah. And I think because we don't require you to install any environment for this assignment one, so it could be better if you download and try to run it on your own computer. Yeah. Let's wait for the rest of the class. Okay, let's start. So, in today's lecture, we are going to talk about structural testing, and and it's also about white box testing. And so here are today's topic. So we will basically cover uh, a new coverage criteria or criterion we are going to use for white box testing. And we are also going to learn about the limitations of structural testing. And then we learn a little bit of data flow testing. So, so before we start our main content today, let's have a quick recap of what we have learned so far. So for white box testing, we know that the most important thing is how do we measure the test coverage with regard of the code we are executing. And all the coverage metrics are coming from a graph called control flow graph. And we have learned three different types of coverage metrics in our last lecture. The first one is statement coverage, which is basically the basic blocks and all the statements inside the control flow graph. And we also learned branch coverage, which is related to covering all the edges inside this graph. And we also learned condition coverage. So conditions are kind of related to branches, right? However, the difference is that if there are conditions used for some expressions or some statements, we are also considering those conditions, not only for the branches. So all these three different types of coverage metrics are focusing on single elements. So either we are focusing on the basic blocks or we are focusing on the branches. So we are not training up different elements. So however, in practice, when we execute the program, we are not executing, let's say, only the statements or only the branches, right? We are executing a mixture of nodes and edges in the control flow graph. So all the test cases actually, in practice, they are executing certain paths inside this graph. So why don't we just use the different paths in this control flow graph as a new coverage metric? And that actually gives us a new coverage metric, which is called path coverage. So it requires actually all the paths through the control flow graph are covered. And each path is actually made up of a sequence of nodes and edges on this control flow graph that are executed during the test case execution. And because it's a sequence, so the order actually matters here. So inside the loop, for example, if we loop once inside the loop, which execute BB2 and BB3 this time, and then we loop again inside this loop, we encounter BB2 again. In this time, the node, the second time of execution of basic block 2 is considered as a different path from the execution in the first run of the loop. So sequence of execution actually matters here. And let's use a question to warm you up with the identification of path from the control flow graph. So how many test cases do you think do we need to cover all the paths inside this control flow graph? So actually this program in our last lecture, we also used this example. So, but instead of doing a path coverage, we were talking about doing branch coverage. We were also using this example for basic block or statement coverage. So in our previous example, we can use one single test case to cover all the basic blocks, right? Can you still remember that? So, so basically what we can do is we can use one single test case to cover all the basic blocks with a loop. We can also use one single test case to cover all the branches, right? So what about paths? How many test cases do you think do we need to cover all the paths here? So remember, a path is like a sequence of nodes and edges which are covered during execution. So, and a path is considered unique if the nodes and edges are the same, right? If two paths are considered the same if they have the same number, if they have the same nodes and edges covered, and they are covered in the same order. And if the length of the path gets changed, it's considered as a new path. So how many test cases do we need to cover all the paths in this program? Actually, the correct answer is 4, more than 4, because we have a loop here. We have a loop here, and this loop could be very, very long, right? Could loop many times, and this okay, it's present. So because we have a loop here, we have a loop here, and this loop can execute an infinite amount of times. So each time we enter the loop, we get a new path actually, because let's say we use BB1, 2, 3, 4, 5, and 2 and 6. This is a path, right? 1, 2, 3, 4, 5, and 6. This is a path. And if we enter the loop twice, we get a new path: 1, 2, 3, 4, 5, 6, 5, 1, 2, 3, 4, 5, 2, and 3, and 4, 5, 2, 6 again, right? Each time we enter the loop, we get a new path. So there's actually an infinite number of paths for this loop, for this program, for this simple program. And assume that we limit the loop to 100 times. So can you imagine how many paths do we get from this assumption? If we assume that this loop can execute at most 100 times, so how many paths can we get? Each time we enter the loop, we can get two possibilities here, right? So because there's an if branch here, so every time we enter the loop, we may either choose to execute 4, or we can directly jump to 5. So each time we enter the loop, we can have two different paths. So if we loop 100 times, we can get 2 to the power of 100 potential paths, right? So, and that is this number. It is very large actually. It's 1 point something to the 10 to the power times 10 to the power of 30. And assume that we can execute 1,000 test cases per second. And this will take us 4 times 10 to the power of 19 years to finish executing all the test cases, covering all the potential paths. And guess how old is our Earth? So the Earth is actually only 4.5 billion years old, which is very, very old considering the lifespan of humans. But it is not long enough for us to run all the test cases here. Like a billion is like 10 to the power of 9, right? It's far from enough for us to execute all the test cases. So it means that it is infeasible to cover all the potential paths of a program. So even if we have a very simple program like this, where we have only one loop and one branch inside the loop. So even for this simple example, we cannot cover all the paths. So theoretically, path coverage is the strongest coverage metric for structural testing. And because it is unlike the statement coverage or branch coverage or condition coverage, which only care about single elements, path coverage can actually represent the interactions between different individual elements, right? Because we are training them up. However, generally, this is, as we have just seen, it is impossible to achieve 100% of path coverage because loops can give us an infinite number of path variations. So each time we enter the loop, we get a new path. And even if we bound the number of loop executions, the number of potential paths could still be infeasible for us to exhaustively try out because there could be branches inside loops. And each time we enter the loop, the number of potential paths will grow exponentially. So even if we bound the number of loop executions, it could be we can still get a very, very large number of paths for us to try out. So generally, this is it's impossible to use path coverage in testing. However, are there any ways for us to get some of the benefits of path coverage without the huge, potentially very huge cost? So let's think about it. So this is about we are talking about infinity here, right? Like we could have infinite number of paths. And the last time we encounter infinity, can you still remember when is the last time we encounter infinity in this course? Like have we even encountered infinity before in this course? No? For black box testing, do we encounter infinity? Because for black box testing, the input space is considered as infinite, right? Because for black box testing, we don't have access to the actual implementation of the program. We only have access to the specifications. And what we can only control is the test input. And a program, we can actually input anything to a program, right? So the input space is considered as infinite. And how did we deal with infinity for black box testing? How did we deal with the infinity in black box testing? We tried to do partitioning, right? So instead of exhaustively try out every potential test input, what we did was we tried to use some metrics to partition the entire input space. For example, we can use boundary values to do this partitioning. We can use equivalence classes to do partitioning. And here, we can also use the idea of doing partitioning to deal with the problem of infinity for path coverage. So we could have an infinite number of paths for us to try out. However, what we can do is, instead of trying out every potential path, we can somehow try to partition the path and try to only execute or only test those representative paths for each partition or for each group. So this is the idea here. And following this idea, this gives us some strategies for doing path-based testing using some variations of path coverage. And the first variation we are going to use is called boundary interior coverage. So remember, what we want is we want to partition the infinite set of paths into a finite number of classes or groups. And boundary interior coverage actually groups the paths that differ only in the subpaths when repeating the body of a loop. So inside the body of a loop, there could be different subpaths, right? Because of the branches inside the loop. So we only care about the paths. We can group the paths that has the same subpaths inside loops together as one group or as one class. So, and then we can select a representative path from each group for testing. And the basic intuition here is like if we execute a loop for many times, and it will give us a different loop. It will give us a different path than executing the loop for just a few times. But we may execute the same subpath inside that loop repeatedly, and this is somehow meaningless. So we only care about unique subpaths that could be executed inside a loop. And let's have a look at an example of how this works. So remember, we only care about the subpath of the body here inside the loop. So we only need to cover each, in this example here, we have one loop, right? And we have, how many subpaths do we have inside this loop? How many subpaths? Inside this loop. We only have two, right? So this one is the first subpath, and this one is the second subpath in the loop. So we have two subpaths in the loop now, and we only need to cover each one of them once with our test suite. So how many test cases do we need now in order to do this? In order to cover each one of them at least once. So how many of them? How many test cases do we need? I see that all of you look quite confused. It's like we only need one test case to cover all the subpaths at least once because of the loop. So we only need to cover this and jump out here. So we only need one test case now because we just want to cover each subpath once inside the loop. So we don't care about how many times do we loop. We just care about whether each one of the subpaths gets executed at least once. So this is boundary interior coverage. And this is an example for us to do this, to cover all the subpaths. So let's come with a more complicated example. So can you identify all the subpaths in this loop? We can do it systematically actually because this is like a graph and we can use different strategies to explore the graph, right? So let's try to do it together here. So the first one is ABM, right? So because we only need to care about the subpath of the loop. We don't care about A here. So we just start from B and we get BM is the first subpath. And then we explore this. This is another subpath, right? Because we only care about what's inside the loop. We don't we don't care about whenever we are getting back to the start of the loop. So the second one is B, C, D, F, L, and then we go back to B. And the third one is our last branching point is D here, right? So instead of exploring the left-hand side of B, we can explore the right-hand side of B. And when we encounter G, we explore the left-hand side first. And then we get this subpath, right? So it's B, C, D, G, H, L, and then we go back to B. And similarly, the last decision point is G. We can explore this subpath, right? And this gives us another subpath. And repeatedly, we can also diverge our execution here at point C. And when we encounter G, we explore left-hand side first. This will give us B, C, E, G, H, L. And similarly, we can get the last subpath by executing the right-hand side of G. So we can get this. So did we just do BFS or DFS just now? This is not an algorithm course, but I hope you can answer this. So what strategy did we use just now, like a DFS or BFS? It's actually a DFS because we are reverting the decision at the latest decision point, branching point. So it's actually a DFS. And similarly, because we are exploring a graph, you can also try out BFS as a practice if you are interested and if you have spare time apart from doing your assignment. So you can try out on your own to explore all the subpaths inside this loop. And there's a special case, however. If M is just an exit, then it is not considered as a subpath. Otherwise, it is. So here we assume that M is a basic block that contains at least one statement. So you may wonder, okay, what is an example of M being just an exit? Actually, we have seen this in our previous slides here. So because we need to know that when a loop gets terminated, right? So in the control flow graph, so there could be some cases where there's a basic block for the exit of the loop without any statement. So if M is something that has no statement inside, we don't consider it as a subpath here when we design boundary interior coverage test cases. So boundary interior coverage actually helps us to remove the infinite loop-based path, right? Because we don't care about how many times do we execute a loop. We only care about whether we can cover each subpath at least once. So, however, the number of paths through the code or inside the loop could still be infeasible for us to test out. because whenever we have a branch, whenever we have something like an if, we will double the number of potential paths we need to execute. So for boundary interior coverage, the number of paths could still be infeasible for us to test out. Because if there are many, many branches inside the loop, we still need to, we may still have a lot of subpaths for us to try out. So there are still problems with boundary interior coverage. And so we may need to apply some additional restrictions on the path we should execute. And this gives us a second variation of path-based coverage, and it is called loop boundary coverage. And it is also focused on the problems related to loops, of course, and it covers the scenarios which are representative of how loops could be executed. So just now for boundary interior coverage, we don't care about how many times a loop could be executed. Here, we don't, it is like a complementary strategy for boundary interior coverage. So here, instead of caring about the potential subpaths inside the loop, we only care about how many times a loop could be executed. So here, the strategy of developing test cases according to loop boundary is like this. We can write a test case that will skip the loop entirely. This means that we are executing the loop 0 times. And then we can also write a test case that can execute the loop exactly once. And then we can write some test cases that can execute the loop 2 or more times. And optionally, we can select an upper bound for this loop execution and select some special values to test out. So if we select an upper bound n, we can try to execute the loop m times, where m is larger than 2 and smaller than n. And we can also write test cases that can run the loop n-1 times, exactly n times, and n+1 times. So does this sound familiar to you? So the values here of times we execute the loop, is this familiar? Is this similar to something we have learned? Yes, boundary, you got the answer. So this is actually similar to boundary value testing. You can see that we are not randomly choosing these numbers. We are actually systematically trying out things. So the im here is like the normal value for boundary value testing. And here, n-1 is like a small value that is valid. A value that is valid and it is within the boundary of a test case, and n is exactly on the boundary, and n+1 is a little bit invalid. So that is why this is called loop boundary coverage. So we care about the boundary values of how many times we could execute a loop. So, however, as you can see from the definition here, this applies only for simple loops, and this looks quite simple, right? So we can write test cases that execute the loop 0 times, 1 time, or 2 or more times. So this is very simple, and this only applies for simple loops. Simple loops means we only have one loop, and the loop condition is independent from other loops, which means that there's no nested loop here, and there's no consecutive loops which could affect each other. So So we will discuss how do we deal with more complex scenarios later. But let's have a look at why this loop boundary. Let's look at a different representation of the CFG for dealing with loop boundary coverage or loop-based testing here. So this is related to one of your assignment questions, actually. So when we are given a control flow graph like this, we can actually unfold this control flow graph according to the loop here. So the basic idea is, let's say we limit the iterations to 3 times. What we can do is we can just copy and paste this part of the code a few times, and basically just simply unfold this control flow graph and get something like this. So this actually can help us to have a better look at the actual coverage of our test cases. For example, if we have some test case that execute pass 1, or the left-hand side pass in the left-hand side pass in the first iteration, and then the second pass in the second iteration, and the third one we execute the left-hand side. So this unfolded control flow graph can help us to have a better look at what's happening in between loops. So this is just another alternative representation of control flow graphs when we have loops, and just to help us to get a clearer view of what's happening in between loops. So this is unfolded control flow graph. And just now we mentioned that the strategy of using some special boundary values of how many times do we execute a code, or do we execute a loop, is only applied for simple loops. And what if we have nested loops like this? We have one loop at basic block B, and we have another one at basic block F. So how could we design our test cases in this case using loop boundary coverage? So what we can do is we can execute similar strategies for each level of the loop here. And we should start from the innermost loop, and then we can try out to execute the innermost loop 0, 1, or 2 times. And then we can move one level up and execute the outer level of loop 0, 1, 2 times, and so on. So this is how we deal with nested loops. So in this example here, what we can do is we can focus on executing F, the loop at F here first. We can execute it once, because here we don't have the choice of skipping this loop. So we execute it once, we execute the loop twice, we can execute the loop 3 times, and so on. To design the boundary value, we can use the boundary values. And then after we finished designing the test cases that can execute the innermost loop, we move one level up. What we can do is we can, for this test case, we can continue the execution here by executing the outer loop in B here twice, in B here for 3 times, and so on for each one of them. So this is how we deal with nested loops. And there are another case of concatenated loops. So if the loops are independent, then it's very simple for us. We just test them one by one. And by independent, I mean that the loop condition is not affected by the other loops. So, however, if maybe the loop condition of the second loop is affected by the code logic inside the first loop, then we can follow a strategy of how we deal with the nested loop. So what we can do is we can start with the bottom loop, which is kind of controlled by the logic of the previous ones, and try out the strategies of developing test cases that can execute the bottom loop 0, 1, 2 times, and we can move one step upper, and so on. So this is similar to how we deal with nested loops. And basically, it's just a bottom-up strategy. So we identify the one which is being affected by all the others, and then we can move on. So apart from the intuition of what we have learned from boundary value testing, like when we design the loop boundary coverage, we are inspired by the design of boundary value testing, so we can test some boundary values of the loop. Another intuition for us to use the strategies of boundary interior coverage and loop boundary coverage is from the formal verification aspect. So in order to prove the formal correctness of a loop, we would like to what people would like to do is they would like to establish preconditions, postconditions, and invariants that are true for each execution of the loop, and then they prove that these conditions will hold with the particular implementation of that program. And if you wonder what is a precondition is the program state or the program context before the execution of the loop. So it's basically, you can consider it as all the potential values of the variables before executing the loop. And post conditions are like all the values for the variables after executing the loop. And the invariants are the values that doesn't change across different executions of the loop. So they are called invariants. And for formal verification, what people do is they try to identify these conditions and then prove that, okay, for this loop, it works. And why we care about formal verification here is because we just introduced in our introduction lectures that formal verification is considered to be one of the strongest means for ensuring software quality, right? Because it's formally proved that a program will behave in certain ways. So the strategy we just introduced actually echoes the idea of formally how people formally verify the properties of loops. So the loops execute, if the loop execute 0 times, which means that we are not entering the loop at all, right? So it means that the post conditions must hold in advance. So post conditions are the conditions or the context of the program after we execute the loop. And because we are executing the loop 0 times, so it means that these post conditions are true in advance. And the loop invariant are the variable values which doesn't change across different runs of the loop. And it is true if we execute the loop once, and if it should also be true when we execute the loop for many times. So that's why we choose the value of 0, 1, 2 for the loop boundary coverage. And of course, we can also use the invariant and the negation of loop condition to imply the post condition, because the invariant shouldn't get changed even inside the post condition, and the loop condition should be negated in the post condition in order to get outside the loop. So these are the these are the strategies. So this is an explanation of why we use 0, 1, 2 for the boundary values. So it's not like randomly chosen. So it's because we are trying to systematically echo the strategies used for formal verification. So it's not a random number 0, 1, 2. It's not random. So it's chosen because of these reasons. So just now we mentioned two strategies for dealing with loops, and there is another partitioning approach for us to deal with the infinity problem of path. So just now for boundary interior testing, we care about the subpath within a loop. However, you may think about, okay, what about the subpath outside the loop? So in this case, we have a new strategy which cares about the subpath of the entire program. And this strategy is called LCSAJ, which stands for linear code sequences and jumps. So based on this coverage metric, a subpath is a piece of code that is executed in sequence until it reaches a branch or a control diverging point. So basically, each subpath you can consider it as a sequence of code that will always execute together. So without any branches in between. So it's considered a subpath, and like a single subpath represents like one linear segment of the program. So because that segment of code will always execute together. So this is the basic definition of LCSAJ. And let's have a look at an example here. So remember, in this definition, J stands for jumps. So given a control flow graph, what we need to do is we first identify all the potential jumps. So inside this control flow graph, we have three jumping points, right? The first one is where we are jumping, where we are ignoring the loop at all. So we don't enter the loop at all. So this is jumping point 1. And jumping point 2 is an if condition inside the loop. And jumping point 3 is where we get back to the start of the loop. So, and this jumping point 3 is actually similar to goTos in assembly code or C code. So the first subpath in this example here is actually from the entry point to B1 to jumping point 1, right? So from the start and end of each subpath is where the program starts, ends, or jumps. So the first one is from entry point to jumping point 1. And what are the sequences? What are the basic blocks inside this sequence? From entry to J1, what are the basic blocks? B1, B2, and B3, right? So can you identify a second code segment here? We can start from entry point to any jumping point. So what we can do is we can have from entry point to J2, right? So this will give us B1, B2, B3, B4, and B5. And what about the third segment here? Entry to J3, right? So this will give us B1 up to B7. And what about some other subsections, some other sub-segments or subpaths inside this? So we can start from any jumping point to another in order to get a sequence of subpaths. So we can start from J1 to J2, right? So if it's the first one is we can start from J1 to the exit point of the program. That's very obvious. And we can also try to get the segment of executing from J1 until J2. So we can get the J2 and J3. Sorry, I messed up with the sequence here. We can also get J2 from J3, and we can also get J3 from J2 back, and we can also get J1 until J2, and so on. So these are the subs. We can try to combine different entry points, exit points, and jumping points together to extract subsequences or subpaths from the program. And you can see that this actually somehow forms some kind of coverage here we could use for designing test cases, right? We can design test cases that cover each of the scenario here. So this could be used as a coverage metric, and we can develop test cases according to this coverage. And we can require the coverage of all subsequences of these different individual components of length n, which means that we can chain different subpaths together. For example, we can execute from entry point to J1 and from J1 to return. We can chain them up together into a larger subpath. So if we allow chaining of two subpaths, it means that we are using the number of 2 here as n. So if we set the number of n is to 1, then this coverage is actually equivalent to statement coverage. So which means that we are not repeatedly executing the subpath. And if we set the number of n to be 2 here, it equals to branch coverage. So it's like we are chaining two subpaths together. And because each subpath ends by a jumping point, if we chain something from, let's say, B1 to J1 and J1 to J2, then we can get the branches here. And if we chain B1 to J1 and J1 to exit, then we can get the false branch here. So if we allow the chaining of two individual subpaths, it means that we are actually doing branch coverage. So the higher the value of n it is, the stronger it is, or the closer it is towards full path coverage. So LC-SAJ actually gives us control over how much or how many passes do we want in the end. And we can define a threshold that offers, because this n allows us to somehow control the number of paths we can get in the end. So this can give us we can set a threshold with the number of n here. So just now we learned 3 different strategies or 3 different types of coverage derived from path coverage. Let's practice the usage of these coverage strategies with an exercise here. So let's reuse the search function we used in our last lecture. So basically, this function accepts 3 values. The first one is a string. The second one is the length of the string, and the third one is the character we are looking for inside that string. And this function will return either the index of the string, of the character in that string, or -1 if the character is not inside the string. So let's try to generate test cases for boundary interior coverage. So do you still remember what do we care about for boundary interior coverage? What's the difference between boundary interior coverage and loop boundary coverage? Okay, look quite confused. So boundary interior coverage is like, as indicated by the name, we care about the interior, right? We care about what's happening inside loops. And what could we have inside loops? We could have subpaths inside loops, right? So for boundary interior coverage, what we need to do is we ensure that each subpath inside a loop is executed at least once. So we care about the interior here. So before we ask the question, so is there any loop inside this program? Yes, right? There's a while loop here. Can you see? Okay. So there's one loop here, right? There's only one loop here. And how many subpaths do we have inside this loop? How many subpaths do we have? Two. Okay, great. We have two subpaths inside this loop. So one is here. The other one is here. So this, although this one is an exit point, it's not the same as simply exiting the loop because it has a statement inside. So it should be counted as a subpath here. So we have two subpaths. So we have two. And we can create two test cases for each of the subpaths here. Or we can use one test case that can loop back and execute the subpath with by entering the loop two times. Can we do that? Actually, we can. We can write a test case that can enter the loop once to execute this subpath and loop twice. So we have two subpaths. We can develop a test case for each one of them. However, if we want to reduce redundancy, we can just use one test case here. We can just use one test case. So let's practice. Okay, you can see a QR code pops up. And let's practice loop boundary coverage. So do you still remember what do we care about for loop boundary coverage? So as indicated by the name, we care about the boundaries of loops, right? We care about how many times do we execute a loop. So here we only have one loop. That is good. So the question here is, because for loop boundary coverage, we care about executing the loop 0 times. We care about executing the loop at least once, exactly once, and we care about executing the loop 2 or more times. So for this example here, is it possible for us to execute the loop 0 times? Which means that, is it possible for us to skip entering the loop when we reach basic block 7? Is it possible? Yeah, 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 you got the correct answer. Before I think even before some others finishing the, so sorry for spoiling the answer. Okay, there are many responses. More than I was expecting. Actually, the correct answer is no, it's not possible. So let's have a, sorry, this screen, this presentation is not. Okay, so it's not possible for us to execute the loop 0 times when we reach basic block 7 because of the conditions of the variable values we have accumulated when we reach basic block 7. So let's have a look at why. So when we reach basic block 7, so what controls whether we will enter the loop? Which are the variables that we need to care about when we think of when we try to think whether this loop could be entered or not? What are the variables here? So we only have 2 variables, right? Yes, yes. You are spoiling the, the answer here. Okay. So we only care about index and n, right? So the value of n here, in order to reach basic block 7, we have to make sure that n is at least 2 because of the restriction of basic block 6. However, this value is also, this condition is also determined by the value of index. And index is initialized as 0, and it is never increment, and it doesn't increase during this execution, right? Until we reach basic block 10. We never increase the value of index. So here, when we reach basic block 7, index is always 0, and n should be larger than or equal to 2. So this condition is always true when the first time we reach basic block 7. So it's impossible for us to execute the loop 0 times. And is it possible that we enter the loop just once? Not possible? It is actually possible, because although n equals to 2, this program is illy written actually, because we can exit here without entering the loop for a second time. So can you imagine what is the test case for executing the loop just once? So we enter the loop, and then we immediately return from this function. So that is, can you imagine the case without looking at the slides? Yes, actually it's like we have a string that has at least 2 characters, which means that n is at least 2. However, the character we are looking for is exactly the first character of the string. So index is still 0, right? And what we are looking for has been found. So we just return the index of 0. So this is how we can exactly loop once inside this program. And of course, we can loop twice. So in this case, for loop boundary coverage, we cannot write a test case for executing the loop 0 times. However, we can write test cases for looping once and looping twice. Okay, so that's about the different strategies for path-based testing. And before we jump into the second half of today's lecture, let's have a 10 minutes break. Okay. All right, let's start the second half of today's lecture. So the second half, so just now we have learned that we learned a new metric for white box testing, and that is a combination of different single elements from the control flow graph, and that is called path coverage. However, we also quickly learned that path is kind of infeasible to use in practice because there could be an infinite number of paths in even for a very simple program as far as there is a loop. So we have to deal with loops, and we learned three different strategies for using some variations of path coverage. The first one is boundary interior coverage, which is related to executing the subpaths within loops. And the second one is called loop boundary coverage, which is related to how many times do we execute certain loops. And the last one is LCSAJ, which is about how do we identify and combine different subpaths to build a coverage metric. So now let's learn, like how we learned the limitations of functional testing, let's learn about the limitations of structural testing. So the first one is quite obvious. So there is the infeasibility problem of developing white box or structural test cases. So we could see that many of the strategies we have learned just now could give us an exponential amount of test cases or tests. So there are several situations where we couldn't apply, and there are some additional sources for infeasibility here for doing white box testing. The first one is like what we have seen from the second poll today, the second practice we did today. So there could be impossible combinations of conditions. So just now we learned that when we try to do the loop boundary testing for the search function just now, we couldn't find a suitable test case that can execute the loop 0 times, right? So it's because there could be some conditions which will lead us to impossible cases. So there could be some situations where we have impossible combinations of conditions. And in some of the cases, there could be unreachable statements for inside the program. And one of them is from the defensive programming, which means that we are trying to be very, very conservative. We try to capture all the potential errors that may not even occur in practice. So this will give us to some unreachable code. And in this case, if certain code is unreachable, then we can never and if we consider their existence when we try to design test cases, we are kind of introducing redundancy. And if these unreachable statements are particularly complex, we are introducing some kind of infeasible test cases. And there could also another source of unreachable statement is like the dead code in legacy applications. Like for example, if we update the version of the code, we may have some code which are no longer used, right? So these are considered dead code, and they are never usable again. And there could also be some inaccessible portions of the code for off-the-shelf systems. So which means that, for example, most of the software we use are cross OS, which means that they could be executed on Windows, it could be used on Linux or Mac OS, and they have some OS-specific code which could only be tested under a certain environment. So those are inaccessible considered. So this is another source of or unreachable code which couldn't be tested for white box testing. So these are like the sources for infeasibility here, apart from the path or test case explosion problem. And this is how we could usually address the, the infeasibility problem caused by unreachable code for structural testing. So what we can do is, because we can collect coverage, right? We can somehow measure the adequacy of the coverage we have achieved. So what we can do is we can we can define a threshold for the coverage. So let's assume that we think maybe 60% of code coverage or statement coverage is good enough. Then once we achieved 60% of branch coverage or code coverage, then we just stop testing. However, this uh, this threshold is normally empirically determined. So the larger the threshold it is, the more budget it requires. And however, if we lower the threshold, we may miss some bugs. So the determination of this threshold is also sometimes problematic. And another thing we could consider in real world scenario is that not every piece of code is equally important for finding bugs. For example, sometimes we can assume that the more complex a piece of code is, the more likely it is to be buggy. So we can focus on certain part of the code instead of the entirety of the software. So that's also a potential solution here. And we can also provide some manual justification of why we would omit some of the scenarios here. For example, we can try to identify the dead code inside a program manually so that we don't need to write test cases for those dead code. We can also try to identify those OS specific code inside the program, and then we can ignore them. But this could be very, very time consuming because it involves manual effort. So finally, what's the answer provided by the industry or most of the company for determining when the testing is done is either when the money is used up for doing testing or when the deadline is reached. So maybe the company promised to release a piece of software by the end of this month, then they have to release that software before the testing is done. So it's all about budget, the budget we have again in practice. So we have learned many different coverage metrics that could be used for structural testing. And now let's have a comparison of these coverage metrics. So let's compare the potential budget required for these. So basically the statement coverage is normally requires the least number of test cases, and branch coverage could require more computational power or could end up in more test cases. And LCSAJ is a special case because when we set the number of n equal to 1, which means that we are not combining any subpaths at all, it means that it actually is equal to statement coverage. And if we set the number of n for LCSAJ to 2, it means that we can combine two subpaths together. Then it is equal to branch coverage. And if we enlarge the number of n, it could get closer to path coverage. So this LCSAJ is a special case here. And we also learned loop boundary testing. So normally loop boundary testing requires fewer test cases because we only need 3 different test cases most of the time, right? For each one of the loop. So we execute the two 0 times, 1 times, and 2 times. And for boundary interior testing, it could be impractical. So although we only care about the subpath in each one of the loop, there could still be many paths. So do you still remember why this could give us so many test cases? Even if we just want to execute each subpath once, we still may end up in too many test cases. Why? Not because of the loop, because we only care about the subpath. We don't care about the case where we loop back. We don't care about the number of times we loop. It is because inside the loops, there could be branches, right? And every time we encounter a branch, we double the count of paths we have. So the number of test cases required for boundary interior testing could still grow exponentially. And that's why this could be impractical. And of course, path coverage is kind of considered as impractical and the most expensive metric here. And apart from the coverage metrics according to the structure of the control flow graph, we can also try to think about the condition coverage. So the basic condition coverage is kind of similar to branch coverage. So we just collect the conditions from the branches and also the conditions from the expressions and of maybe value assignments or variable declarations. So it's kind of similar to branch coverage. And of course, we can use both branch and condition coverage together. And for MCDC coverage, it requires more test cases because we need to consider different combinations. And for compound condition coverage, it is kind of impractical in most of the cases because we need to have the Cartesian product of each sub condition for most of the decisions. So that's why it could be impractical in this case. And let's continue. So another big, and apart from the practical concerns, from the theoretical point of view, there is another limitation for structural testing we have learned just now. Because all the coverage criteria we used are coming from the control flow graph. And in our last lecture, we mentioned that there are two types of graphs within a program. And what are the two types of graphs? Can you still remember that? So the first one, we are very familiar with control flow graph now, right? And the other one is data flow graph. So we are not considering data graph at all. So the rationale of using control flow graph based coverage metric is that we assume that we can never find a bug within a statement if we don't execute that statement. And this is true. However, is the reverse true, which means that if we can execute a statement, we can certainly find the bugs inside that statement. Is the reverse one true or not? Is actually not true because executing a line that contains a fault doesn't guarantee a failure. And here is an example. So for example, if we write a condition like this, the desired condition is A should be smaller than or equal to B. And if somehow we made a typo, if the developer made a typo, like by writing the smaller than to larger than. So this time the code becomes A is larger than or equal to B. And if we write our test case as A equals to B and execute this condition here, the program will behave the same, right, with the correct and wrong implementation. So even if we can execute a line of code that contains some error, we may not be able to expose that error. We have to consider how did we reach this line of code? Like what values do we have when we are executing this line of code? So, but control flow graphs cannot give us the answer of which values do we have when we reach certain point. It is not enough. So the observation here is just executing the code is not enough for finding all bugs. This is not enough for finding all bugs. We need to, it depends on how we reach certain point of the code. And we need to care about the values and data. So that's why we also need to consider data flow when we design test cases for white box testing. However, in this class, we still focus on the usage of different metrics from the control flow graph, and we just do a brief intro of how could we use data flow for testing. So data flow is like providing another view of the program. So control flow graph is like we are considering the program statements as commands that could cause the program to transit between different states. So the commands are helping the program to transit from different states. And for data flow point of view, we are viewing the program statements as a computation and transformation of data. So what we care about is how data is passed through the program. So it is all about reasoning between data dependencies. So if we observe a variable is used in certain statements, what we want to know is where does the value of this variable come from? And we also care about, is the value ever used anywhere inside the program? Is the variable properly initialized? And if we change, if we assign a value for a variable, which else part of the program could be affected by this value assignment? So these are some examples of some example questions we care about when we do data flow analysis. So like I just mentioned, we just do an introduction to data flow analysis in this course because it is covered by some other courses here in UNSW. And for data flow, you may encounter two typical concepts, which are definition and use. So we say that a piece of data is defined when we encounter these cases, we are like, if we have variables as declared or assigned values, then a piece of data is considered as defined. So this is data definition. And a piece of data is considered as being used when these variables are used for performing computations. So this is the def-use relations could help us to capture the flow of information or the flow of values through the program. And according to this definition here, inside the program, Whenever a variable is declared, initialized, assigned with values, or received as parameters for a function, then we consider that, okay, a new value is defined. And whenever a piece of data or a piece of value is used in expressions, conditional statements, parameter passing, or parameter passing means invoking function with particular value, and or it is used in some kind of statements like the return statements, then that piece of data is considered as being used. So let's have a look at an example of how definition and use are defined in this simple program. So this program actually helps us to calculate, given a list of numbers, this thing actually helps us to calculate the min and max value of that list of positive integers. So inside the first line, I'll give you an example and let's try to do the rest of them according to this example. So here we create or we declare the variable of mean here. So this is a definition of variable mean. And what are the def and use for line 2 here in this program? We are defining the value of max, and we are using the value of n here in this program. And what about line 3 here? Are we defining anything here? Yes. So what is being defined here? Mid. And do we use anything here? Max and mean, right? So we define mid and use max and mean. And do we define anything on line 4? No, yes. We use the array of A. Let's assume A is defined somewhere else or passed as a parameter before. So A mid, which is the element of A, is being used. Mid is also being used because it is used as the index for accessing array elements. X is being used because it's in the expression of A mid not equals to S. And min and max are obviously also used. What about line 5? Are we defining anything or are we using anything? We are actually defining the value of mid again. So define is not only about definition, it's also about updating the values. So we are defining the value of mid again, and we use min and max in this line 5. And what about line 7? Are we defining anything in line 7? Yes, right, because we just encountered line 5. We are defining mean here actually, and similar for line 9. So for line 7 and line 9, we are also defining values for min and max. This is like redefining the values. So by considering the definitions and usages, we can build def use pairs for variables. So we can say that there is a def use pair whenever all these conditions are satisfied. So first, there need to be a definition of x at certain location. And then this variable x must be used somewhere else. So this because we want def use pairs, so we definitely have to have a definition and a use, right? And these are kind of by default. And the third requirement is that we have to have a path in the control flow graph from the two locations, from the def location and use location. Otherwise, if there's no control flow graph between the two locations, it means that it is not possible for us to run the program from the def to use. It means that the def use pair doesn't exist. So we have to consider control flow graphs when we try to capture diffuse pairs. And the path should be definition clear for X, which means that in between the execution from A to B, there shouldn't be another definition for X in between A and B. So this is because we can see that we can reassign values, we can update values of variables. For example, for the from 3 to 4, we can say that there's a diffuse pair for mid, right? Because in line 3, mid is defined, and in line 4 it is used. However, we can't say there is a diffuse pair between line 3 and line 6 for mid. That is because it is not definition clear from 3 to 6, because mid is redefined in between this 3 and 6. So the first two conditions are easy to remember. It's like, because it is called def use pair, so we have to have a definition, we have to have a use. And the third one is also easy to remember, because we have to make it feasible, right? We have to make it allow the program to execute from the def to use. And the last one is the variable shouldn't be redefined on the path. So this is diffuse pair. So let's have a look at example with the previous program. So let's try to find diffuse pairs for mean instead of mid, like I used for example just now. Let's try to use mean here. So first, mean is defined at line 1, right? So where else is it used? It's used in line 3. So is there a diffuse pair between 1 and 3? Yes, right. Because we can execute from 1 to 3. And there's no redefinition of, we are not redefining the value of mean in between. So 1 and 3 is a diffuse pair. Can you quickly identify another one from this program? 1 and 1 and 4, right? 1 and 4. So 1 and 4 is another one. And what about 1 and 5? Is it a valid diffuse pair? It is, right? 1 and 5. What about 1 and 7? Is it a valid diffuse pair? No, because 7 is like redefining, right? And since 7 is redefining, we can use 7 as a starting point for finding more diffuse pairs. And because this is a loop, we can loop back to 4, right? So 7 and 4 is another diffuse pair. And of course, 7 and 5 is another one. So these are the diffuse pairs for mean and for this pair variable mean. So since we have something like diffuse pairs, so why don't we use it as a metric for calculating coverage? So what we can do is we can develop two types of coverage metrics from the definition of diffuse pairs. The first one is diffuse pair coverage. The second one is diffuse path coverage. So like coverage is everywhere for white box testing. So we just care about different metrics of how we can calculate or how we can represent code coverage. So the first coverage variation here is diffuse pair coverage, and it requires each diffuse pair to be executed at least once in the program execution. And this could be And we can actually easily achieve structural coverage without covering all diffuse pairs. So even if we can cover all line of code, or even if we can cover maybe all the potential paths of a program, we may miss some diffuse pairs. So because we are viewing the program from two different points of views, like for the structural coverage, they are derived from the control flow graph. However, the diffuse pairs are derived from the data flow graph. So even if we run a program, even if we reach certain point of the program, we may not be reaching that point of the program with the desired values of the variables. So like we have seen from the example of larger than or equal to or smaller than or equal to, right? So we may reach certain line of the code without the desired values. So this diffuse pair coverage can actually help us to capture those errors which couldn't be exposed with the control flow graph based coverage metrics. And the calculation of this coverage is like others. So basically, we just divide the number of exercised or executed diffuse pairs by the number of total diffuse pairs. And the second variation here is called diffuse path coverage. So diffuse path is something like is with regard of the execution path. So like we just mentioned, diffuse pairs, there must be a path connecting the location of definition and the location of use, right, for a diffuse pair to exist. However, there could be many execution paths from the location of definition and the location of use. So what we do with diffuse paths is like we combine the data flow graph and the control flow graph and try to find out the potential execution paths for each diffuse pair and use the execution paths of these diffuse pairs as the coverage metric here. So this is called diffuse path coverage. And this similar to how path coverage differs from the statement coverage or branch coverage. Path coverage can give us like the interactions between different single elements, right? So diffuse path coverage can give us a more comprehensive coverage for the program, and this could have the path explosion problem similar to the control flow graph based testing coverage. So even without the looping path, there could be the number of diffuse paths could be exponential to the size of the program, and that is because this is similar to why boundary interior coverage could give us exponential number of test cases, because there could be many branches which can give us different paths in between diffuse pairs. So for example, we could have a lot of if and else, which can give us a lot of potential paths for a program. For this program here, if we try to capture the diffuse pair between this this parameter receiving here and the usage of this ch variable here, we may have 2 to the power of 6 paths here in between. Sorry, to the power of 7 here. So that's why even if without loops, we could have a lot of paths, and there could be path explosion problems, which makes the diffuse path infeasible in practice. And before we end today's lecture, let's finish the last part of the practical Python syntax, and we only have one part left. And when you implement your assignment code, you don't have to follow the best practice, because we don't really care about your coding style and all those kind of things. But this is just to just to provide you a little bit of additional thing that you may use in the future. So let's continue the very last part. So I think you may have used this a lot when you write your code. So it's like when you have when you have a collection of a variable that is like a collection of values, like for example, the variable is a list, a set, or a dictionary. How can you deal with individual elements of this variable, right? You may encounter this scenario. You want to handle or precise the individual values. So what you can do is you can use a for loop here to iterate through all the elements with one line of code. So for example, if we have a list of integers from 1 to 9, and we want to double the value of each of the integer inside the list, what we can do is, instead of writing a for loop, writing a few lines of code, we can just use one line to update the value here, and we can even use if conditions within this single line of code. So this means if the element is an odd number, then we doubles that number. So this is this single line of code. And similarly, we can also use the Wallace expression, the Wallace operator we have learned previously. And this will save us from defining the variable with another line of code. So this is how we can use the for loop to iterate through the list elements. Similarly, we can also do similar things for the dictionaries. And for dictionaries, whenever we are for strings, and for dictionaries, we can also do similar things, and by default, if we don't write this d.items, if we just for something in a dictionary, what are we looping for here? Let's say we don't have this for kv in d.items. We just have maybe for something in d. So what is the value of something here? For something in d, what are we looping here? We are actually looping for the keys by default. If we don't specify the d.items, we are looping for keys. And this is how we can simplify the writing of the code, or complicating the writing of the code, but it looks clearer if we just use fewer lines. So, and we can also try to do multiple dimension expansion. For example, we have multiple loops. We can for these multiple loops a few times within that line of code, and this can give us this can give us a Cartesian product of all the combinations of these three loops here. So this will give us, for every element of I, we can have a combination of all the possibilities of the single elements of j and k in these other two loops. So this will give us 3 times 3 times 3, 29 items here in the end. So we can have nested loops in this kind of expression here. And we can also try, this is particularly, this is actually similar to how we can use higher order functions to achieve similar things. For example, we can use when you learned TypeScript or JavaScript, I believe you have learned those higher order functions of dealing with lists, right? Like map and filter in 1531. I hope you can still remember that. Yes. So actually, this is like a replacement. This is similar to how we can use map and filter. So instead of writing instead of invoking the map or filter, what we can do is we can just use this simple expression to do similar things. And that's all about the practical Python syntax. And that marks the end of today's lecture. And if you have any questions regarding the assignment one or any lecture content, please come to the help session. It's held in level 5 of the CSE building. So you can come to us. I will be there and Zihao will also be there. So you can come if you have any questions. So that's all for today's lecture, and thank you for coming. Thank you.